changed from a mechanical problem where you had masses and velocities and forces acting that made the points move, like planets in the gravity field. He was trying to represent what was going on in terms of waves. But what you can use, they use a lot of the classical ideas, namely the conservation of energy. They have kinetic energy and potential energy gives you total energy. For example, that would be if we were in this box here, I would have a total, this is a better example actually. I would have a total amount of energy, say. So I would draw that like this. But it's actually composed of two parts. This part is the potential energy. This is the curve I drew here. Parabolic potential energy. Now, if I'm a particle, what I'm doing is I'm rolling around, and here I have a total amount of energy. When I'm at the bottom, I can call that zero potential energy. Now, as I roll up the hill, I lose my, and here at the bottom I have kinetic energy, the maximum, right? We know this sort of thing. Your kinetic energy is the maximum at the bottom. It's like a pendulum swing. Your maximum speed is at the bottom. You slow down as you get to the top. And then you stop, right? And that's called the classical turning point. That's where a classical particle would roll. A friend of the basketball player knows that if you have a upward shot, you have kinetic energy in the vertical direction. It turns into potential energy when you reach the top. At the top, there is no vertical speed, right? So the V in the y direction is zero, but the potential energy is the maximum. Your total energy is the same. You just give kinetic to potential, and now it falls back down, and you're converting potential to kinetic, it picks up vertical speed. So the same thing's going this oppositely in the bottom of the bowl, or if you're rolling up a hill or something like that. So in any case, you roll up the hill, so the total energy is given by a line like this. So the potential energy is this much. Should keep the color code right. This is my potential energy, and the remainder of it here is the kinetic energy. That's what the picture is trying to say. And when you get up to this point, the kinetic energy is zero, but you're all potential. And then you roll back down, and you got potential is zero, but your kinetic is maximum. And then you roll back up, giving up your kinetic to potential. So that's what's happening. Very simple. It's not hard. So that's the kind of story we're trying to replicate here with an equation. And we're going to use some of this information here. So we're trying to make this mechanical problem, kinetic potential energy, into a wave. Now, I'm not sure if you're familiar with the notation, the exponential notation for a wave. E to the I kx minus omega t. Well, this is just sines and cosines. Let's just say 2 pi x over lambda minus 2 pi f t. Okay. The point is that we're trying to make something with kinetic energy, which we said was h bar squared, or h squared, over 2m lambda squared. Now you see there's a lambda over here. This is what I'm trying to bring out in this particular thing, which you can read at your leisure. There's a lambda over here. We're trying to make something with the lambda squares on the bottom. The way to get it out of here is to take the derivative of this. If you take the derivative of the sine of 2 pi x over lambda with respect to x, you get 2 pi lambda cosine of 2 pi x over lambda, right? Okay, see, we're trying to get something like this. Lambda squares on the bottom. By taking the derivative once, we get 1 lambda on the bottom. By taking the derivative again, so we take the second derivative of sine 2 pi x over lambda. Take the derivative the second time. So we take the derivative of the cosine. We had the 2 pi over lambda, and the derivative of the cosine is minus the sine. The sine. Oh, but we have to bring out the 2 pi over lambda. It's very important. Another 2 pi over lambda comes out, and then you get the sine back. 2 pi x over lambda. So when you're all through by the second derivative, you've got 2 pi over lambda squared with a minus sign, sine 2 pi x over lambda. You see, and we're almost there because we're trying to get this lambda square on the bottom. So by just putting some constants in here, I don't know if I can do it right away. I would multiply, for example, this by h squared and 2m. So if I can multiply this by h squared and 2m, okay. I'm getting closer to making this into the kinetic energy. You can see with a little bit more math, I could make that coefficient look like a kinetic energy. Am I losing you? What I'm trying to do is write something like a wave equation, which is going to have a second derivative of some kind of an amplitude with respect to space, because I took derivative with respect to space, and I put some coefficients in front of it. It's going to be h over 2 pi of 2m, and that should give me the kinetic energy times this function again, because you remember when I took the second derivative of the sine twice, I got back sine. So I'm going to get that function back again. I think there's a minus sign here because the sign changed. So the point is that this kind of an operation gives me the kinetic energy. And to make the law of conservation of energy work, so this is the kinetic energy part, I just have to take now the potential energy part. Now I have the kinetic energy part times some kind of a wave function. I put the potential energy part times that same wave function, and that should give me the total energy, again, with some amplitude function. So what I've done, I've constructed, using the law of conservation of energy, as long as I put in this kind of wave-like behavior, I've now got a wave representation of the conservation of energy. So the Schrodinger equation comes down to this thing. I have my kinetic energy part, which is always this minus h bar squared over 2m, with the second derivative of this wave thingy with respect to x. That's the one that brings down the wavelengths. And by bringing down the wavelengths, it brings down the momentum, which is the kinetic energy. Then I simply take u, the potential energy part, times this function, and that will give me the total energy, which is exactly what we say here in classical physics. I have the total energy, which is the sum of the potential energy plus the kinetic energy. And that's the Schrodinger equation, right here. Now, in using this, the interesting part, see, well, here's the derivation I just try to present. Namely, you have this kinetic energy part, and you know that the momentum depends on the wavelength. So if you start with a wave, you see that you can bring down the wavelength parts by taking the derivative twice, actually, to bring down the lambda squared, and then you get this equation. Oh, here, you see I've used h rather than h bar. If you put in h bar, you use a 4 pi squared from here. So it really is h bar squared over 2m, h bar being h over 2 pi. And that's it. So and then we have the idea that we have this function, which is the wave feature, and its interpretation is that it represents the probability that the particle is at a certain place when you square it. Psi squared is interpreted as the probability that the electron is at a certain place. We'll get into this in a little more detail. So for example, if you have particles on a line, you square the wave function, so that gives you the probability that it's at a place x, and then you multiply it by the distance, dx, and that'll tell you the likelihood that it is, if you have psi as some kind of function, you just take the value of psi at x, you square it. So, and then you take the region dx that you're interested in, and if you get psi squared at that point, multiplied by this is the probability that you'll find the particle there. Now, that tells you that you have to do something else, namely the probability of finding a particle someplace cannot be greater than 1. It should be 1 if you look everywhere. In other words, if I look everywhere over space, you get the condition, the so-called normalization, that if the probability of being at some place r is what it is that, and you square it. By the way, we put these magnitude signs because it's possible for the wave function actually to be imaginary. That's okay, because whenever you square it, you make it real. But if you sum that over all of space, then this should be 1. So if you get some kind of a wave, you have to make sure that its integral over all space is only equal to 1. Okay? Because it's got to be someplace, but it can't be, the probability can't be more than 1 that it be at someplace. So that's known as the normalization condition. And also, it has to have a nice simple shape. For example, physically, it's sort of impossible for a wave to have like a value like this. You see, because if you look at someplace, it should be, the probability is either this or that, but you can't have two different probabilities. So you have to have a smoothly varying function. It can vary, but it has to vary smoothly, because it has a single value in any place. Sort of reasonable physical things, because these are supposed to be a physical object. So it has to be normalized, and its derivative has to be continuous so that it has one value at a given place. And the other thing that's important, in order to get normalization, because we're going to integrate from over everywhere, it's reasonable that the wave function has to decrease. So as you go to infinity, the wave function has to decrease pretty rapidly, because you're taking in all of space, so you'll have conditions like this. Okay? Now, I really don't expect you to know how to derive all the different wave functions, but let me just point out to you that the kinetic energy is pretty much the same for all problems. All it is the derivative of this wavy thing with respect to space, the derivative taken twice. What varies from problem to problem is this, the potential. That is to say, what situation has a particle been put in? Is it in a box? Is it in a bowl? Is it in an atom? Is it just hitting a barrier? So that, and all of that is represented by this U, the potential. So this varies from problem to problem. And just for fun, I will move on as quickly as I can here. See, the potential energy describes the different situations. For example, if the potential was 0, we say that's a free particle. It's just a horizontal surface. Or you could have it 0 someplace, and then infinite someplace else, like an infinite well or an infinite barrier. Or you could be a harmonic oscillator. This U could be kx squared. Or it could be in a potential of a Coulomb field, namely like the hydrogen atom. So given the U, you look for the boundary conditions. Namely, it has to go down to 0, and you make sure that it fits into the shape. So let me try to show you, well, the very general way you can look at this. And it's exactly like what we did with the Chladni and the vibrating string. Namely, you always start out with the lowest frequency mode having the longest wavelengths, and you get sort of one half wavelength. Now look at all these different potentials. Here's an infinitely deep well. Look at the lowest mode, half wavelength. You look at the next mode, 2 halves. You look at the next one, 3 halves. Up and up and up if you want, okay? Okay, I can make the problem a little bit harder. I make the well not infinitely deep. Okay, what's the lowest one? Well, it's 1 half wavelength, but it leaks a little bit because it can penetrate this barrier a little bit. Then I have 2, then I have 3, and then et cetera, et cetera. Okay, I look at the harmonic oscillator, parabolic well. What's the lowest mode? What's the next? It's just, they're all the same. That's interesting. You don't have to know that much. Just remember what we saw in the string. The lowest mode is 1 half wavelength. The next one is 2 half wavelengths. The next one is 3. Regardless of the potential, as the energies go up, you have more waves in there. And you look at the hydrogen atom. I'm sure you've seen this. S, P, D, F, blah, 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 all that. It's all the same thing. The S states. You have, this is 1s. Now, so that's one mode. You have 2. In other words, have one time it crosses the line and comes back over here. And here's the third state. It crosses the line here and then crosses back here. So each one is just one node more than as you go up in energy. So your 1s state is the lowest energy. Your 2s crosses, it's a little shorter wavelength. The third one is like that. So that they all have the same pattern. It's just waves in a box of some sort. Okay. Now the one case that you really can work out is the particle in a box, and you have that as probably part of your homework, where you can get that the waves are just 1 half wavelength, 2, 3, and their energies go up as the number of half wavelengths n squared. Okay. And then the other idea is that once you have these levels where the wave can live, the energy changes. You must go to that level, and then when you drop down and emit energy, you drop down between the levels and emit the photons. Okay. This slide is supposed to show you how tiny each photon is. For example, visible light is 10 to the minus 19th joules in each photon. But on the other hand, if you have sunlight, for example, rising from the sun at 1,000 watts per square meter, you have 10 to the 21 photons arriving per second, per square meter. So that's huge. So what is this? It's this rain of tiny particles. But on the scale of an electron, that photon has 10 to the minus 19th joules, but it has that equivalent to 2 electron volts, which is on the scale of an electron, it's pretty good. And the interesting thing is that if you can get give an electron 2 volts, it can drop down and give you visible light, which is what goes on in lasers. See, the electron, even 2 volts from your dry cell, will give you, if you can get energy levels that far apart, put an electron up there, when it drops down, that 2 volts converts into visible light. That's very interesting, very powerful thing. The voltages that we deal with in batteries, little batteries, are on the scale to give us visible light. Of course, with the battery, you boost the electron up to that level, and then when it drops down, it gives you light. We'll go into this much more in detail. I guess our time is up. See you Wednesday. By the way, your exam